This video is featuring the solution for the questions of internal test paper 2 for the subject of computer oriented numerical methods, which is basically an assessment. The first question in the question paper was, what is partial pivoting, and write an algorithm for pivotal condensation. So here's the definition for partial pivoting. From the definition, we interpret partial pivoting as a method in which the pivotal element of the augmented matrix is made highest among all the other elements to solve the linear equations using methods like Gauss elimination. So here is the algorithm for pivotal condensation, where the algorithm is designed in such a way that the value of the first element, first row, is assigned to a variable called max, and a loop is applied where the value of all the other elements of the augmented matrix is checked whether being greater than max. If it is, then the value of that particular row and column is assigned to max in order to make the pivotal element highest among the row. Similarly, we make the pivotal element highest in the second row and in the third row as well. So this is the algorithm for the pivotal condensation. And the second question in the question paper was, explain refinement solution of ill-conditioned equations. What is ill-conditioned equation? So the ill-conditioned equation are equations where a minor change in the coefficient of any variable can lead to a higher to a large change in the solution for the equations. So here is a refinement solution. In this refinement of ill-conditioned equation, we simply perform methods like Gauss elimination, Gauss Jordan, or any iterative method to find out the solution for our given equation of linear systems. And we get the answer for x1, x2, and x3 as x1 dash, x2 dash, and x3 dash. Here, the values of x1 dash, x2 dash, and x3 dash does not satisfy our given linear equations. So, we make another system of linear equation where we assign the coefficients as our new derived values of x1 dash, x2 dash, and x3 dash. And we find out the error by subtracting x1 and x1 dash, x2, x2 dash, and all the other uh, variables in our given system of linear equations and the derived system of linear equations from the solutions we have found out. So this is how we resolve our problem regarding the unconditioned equations. Following this, the third question was to write an algorithm for forward interpolation. So here we first of all take the input of the table for which we want to find the forward interpolation. Basically, forward interpolation is found out by subtracting the value of y2 and y1. So here we take a for loop from 0 to n and take the values of xi and yi. Again, for printing the forward interpolation table, we assign a loop variable j as 1 to n and I as 0 to n minus j, and assign yij as yi plus 1 j minus 1 minus yi j plus 1, and end the loop. And for printing the table, we take two loops where the first loop goes from 0 to n and the second from 0 to n minus I, and print the values of y, I, and j. End our loop. Then we read the value of a and assign the value of x1 minus x0 to h. Here we find out u using a minus x0 upon h. Then we initialize the variable sum and p. Assign y00 to sum and 1 to p. And we run a loop for j1 to n assign the value of p into u minus j plus 1 upon j to p, and assign the value of sum plus p into y0j to sum. End of a for loop, print the sum, and that is the end of the algorithm. Basically, the forward interpolation formula is a f of a plus hu is equal to f of a plus u 1 factorial del f of a plus u minus 1 factorial 2 del square f of a plus up to n terms. The fourth question was to compare iterative methods and direct methods for solving the system of linear equation. So on the basis of nature, the iterative methods involve an initial guess of the answer, whereas in the direct methods, we have finite number of steps where we need not guess any initial value of our solution. On the basis of convergence, the iterative methods required number of iteration to reach the equilibrium solution for our given system of linear equation. Whereas in the direct methods, we have a well-defined criteria where the algorithm will stop. The application of iterative method is that it can be applied to sparse matrix where the number of zeros are more, and we cannot apply direct solution to sparse matrices, but they are good in case of small system of linear equations. The examples of iterative method are Jacobi method, Gauss-Seidel method, successive approximation method. And the example of direct methods are Gauss elimination and Gauss Jordan. Fifth question in the question paper was to write an algorithm for Lagrange's interpolation method, the formula for which is defined as Lix is equal to summation of I from 0 to n bracket of multiplication from 0 to n of the function x minus xj upon xi minus xj into yi. Here the values of I and j should not be equal for the iteration. So the algorithm starts by reading n and x and reading the values of xi and yi. That is the table of the contents. Assign 0 to sum and run a loop from 0 to n where we assign p, which represents product, as 1, and run a loop from 0 to n. For I not equal to j, we assign a new value to p by multiplying p to x minus xj, which divides by xi minus xj. We endeavor for j loop here and increment the sum variable by assigning sum plus p into yi to sum. We endeavor I loop here, bring the value of sum, and that is the end of the algorithm.